This video is for topic 6.6, Introduction to Enthalpy of Reaction. The objective for this topic is to calculate the heat, Q, absorbed or released by a system undergoing a chemical reaction in relationship to the amount of the reacting substance in moles and the molar enthalpy of the reaction. So it sounds complicated, but we're going to break it down. So the standard reaction enthalpy is symbolized by delta RH naught. So the little superscript circle is called a knot, and that goes for standard. The units for this are kilojoules per mole of reaction. The standard state is the most stable form of a substance at 1 bar of pressure and at a temperature. The temperature is usually 25 degrees Celsius or 298 K. So it's whatever state, whatever form the substance is in at 1 bar of pressure and roughly maybe a little warmer than room temperature. Moles of reaction means we need to look at the coefficients when we're thinking about how this reacts. Just like with our other Q values, positive Q means energy absorbed, negative means energy released, and when we reverse the reaction, we reverse the sign. So it takes the same amount of energy going forward and backward, but we use positive and negative to indicate whether the energy is absorbed or released. So if it's absorbed going one direction, it's going to be released going the other direction. So here's our first example. Sucrose can be oxidized to carbon dioxide and water, and the enthalpy change for the reaction can be measured. So the standard reaction enthalpy for this reaction is negative 5,645 kilojoules per mole of reaction. So it's negative, which means that it is exothermic, so we know that, and we know how much energy per mole of the reaction. So the question then asks, what is the enthalpy change when 5 grams of sugar is burned under conditions of constant pressure? So our sugar is our C12H22O11. So let's look at how this plays out. So we're going to start with our 5 grams of sugar, so our C12H22O11, and we're going to convert that to moles because we don't do anything in grams. And so 1 mole of our sucrose is 342.296 grams per mole. And then I'm going to look at my coefficients, and in 1 mole of the reaction, we're going to use 1 mole of C12H22O11 because there are no coefficients, so it's just a coefficient of 1. And then our enthalpy is negative 5,645 kilojoules. So then we cancel out all of our units, we end up with negative 82.5 kilojoules of energy released when we burn 5 grams of sucrose. Okay, here's our next example. The combustion of ethane, C2H6, has an enthalpy change of negative 2,857.3 kilojoules for the reaction as written below. Calculate the delta H naught for the combustion of 15 grams of C2H6. So it tells me that the standard enthalpy change is negative 2,857.3 kilojoules per mole of reaction. I want to know how much energy I'm going to get if I burn 15.5 grams. So I'm going to start by converting my 15 grams of C2H6 into moles. So I'm going to use the molar mass, and 1 mole of C2H6 has a mass of 30.068 grams. And then in this case, there's 2 moles of C2H6 for 1 mole of the reaction. So when we look at the overall reaction, we're going to use 2 moles of C2H6. So we have a 1/2 ratio. And then we use our standard enthalpy of reaction. So negative 2,857.3 kilojoules. And when all of our units cancel and we calculate this out, we get negative negative 713 kilojoules of energy. So when we are calculating, so these are similar, you can think of these similar to stoichiometry calculations. So you have your mass, you're going to convert to moles. You need to look at the coefficient. So instead of comparing two coefficients between two parts of the reaction, you're comparing the overall reaction to the coefficient for the substance you're looking at. And then you have the standard enthalpy of reaction, which will always be in kilojoules per mole. And so you can use that as a way to calculate the amount of energy you get out when you use a certain amount of one of your reactants.